Hello everyone, and welcome to our webcast titled A Guide to Total Performance for Condensers and Heat Exchangers. I'm your host, Darrell Proctor, Associate Editor with Power Magazine. Improving productivity and reliability of equipment and processes is of vital importance to power plants, refineries, and industrial production facilities. It can be difficult to know exactly what you should be looking for when it comes to the care of your units. With total performance, you can anticipate problems and keep your condenser tubes at optimum efficiency. The three-part process identifies the status of condenser tubes, detects equipment fatigue that can cause inefficiency, and cleans the tubes to improve flow and heat transfer. Together, these processes can increase efficiency by as much as 4%. In today's webinar, we will discuss how the implementation of condenser cleaning, leak detection, and non-destructive testing will maximize megawatt output and minimize condenser-related outages during your operating cycle. In this program, we'll hear from Gary E. Fisher, National Sales Manager for Conco Services Corporation, located in Verona, Pennsylvania. Conco is a world leader in offline mechanical tube cleaning. From power generation to polymers, alumina to refineries, Conco technicians have restored efficiency and reliability to more than 150 million condenser and heat exchanger tubes worldwide. In addition to cleaning services, Conco is a leading provider of non-destructive testing services, including RFT, eddy current, and tracer gas leak detection. Before we get started today, I'd like to point out a few housekeeping items. At the left of your screen is an area where you can type and submit questions to Gary today. Feel free to send in questions at any time during today's presentation. We'll try to answer as many as possible during the Q&A portion or by email after the program. If you experience any technical difficulty, please type that into the same area on the left side of your screen, and our production staff will assist you. A certificate of completion for professional development hours will be sent via email to every registered participant who attends. Before we begin, I'd like to thank Conco Services Corporation for underwriting today's program. Their generosity allows everyone to attend this presentation at no cost. Now I'd like to introduce our presenter for today's program. As mentioned earlier, Gary E. Fisher is National Sales Manager for Conco Services Corporation. Gary manages a team of 7 outside and 2 inside sales reps and is responsible for all sales activities within the United States power generation market. Gary holds a Bachelor of Science degree in electrical engineering and also an MBA from the University of Pittsburgh, and is a long-standing member of ASME. He currently serves as chairman of ASME's Heat Exchanger Committee. I'd like to welcome our audience to today's program, and with that, I'll turn it over to Gary.
Thank you, Darrell. I appreciate that, and I want to welcome everybody to our Total Condenser Performance webinar. We know that you have busy schedules, and so we appreciate the time that you're making to attend, and hopefully at the end of this process and this presentation, you'll be able to take something home that will be able to help you in your particular application at work. So the question that we're being asked and thinking about during work hours is, how can I raise plant efficiency and yet lower production costs? Well, welcome to Total Performance. And what is total performance? It's when we're able to take cleaning, eddy current testing, and leak detection into the same program, maximizing the efficiency and the effectiveness of our condenser or of your condenser. If you implement these strategies, you'll be able to maximize megawatt output and minimize the condenser-related outages, especially those emergency outages that you run into whenever you are trying to push the unit to maximum efficiency and effectiveness. So to move forward, what we're going to talk about in this presentation are 3 sections. We're going to talk about fouling and condenser cleaning. We're also going to get into air and water in-leakage testing, and we're going to talk about eddy current testing. And hopefully during this process, you'll be able to learn a little bit more about your situation, your condenser, where the water's coming from and what it's doing inside your condenser, and how you can help to alleviate some of those issues. If we jump into the fouling 5, as we call it, Basically, anytime you start your condenser up, you begin the fouling process. And whatever is in that water source that you're bringing in through that condenser begins to foul in the condenser itself. So fouling begins immediately. And we have divided this down into what we call the fouling 5, which are 5 categories that you fall into. 1, deposition or particulate fouling. 2 was a scaling or crystallization. 3 would be microbiological. The 4th is debris and macrofouling. And finally, corrosion and corrosion products. Now, you may have one or more of these types of fouling within your particular condenser based upon what type of water you have going through the condenser itself. So let's talk about each one in a little more detail so that you get an idea of what we are speaking of when we talk about each one. Deposition or particulate fouling, what is that? That's a particulate or debris that settles on the tube surface. It could be mud, it could be silt. A lot of times it's pulled in from the bottom of the river or the bottom of the pond or the lake that you're pulling in from. Low flow conditions, you can pull this in. It's a natural sediment. It's very moist and wet. And so what happens when you get this into your system is that you see a heat problem. You're not transferring heat properly. It is non-conductive of heat. And so you immediately see that heat reduction. And of course, by having this on the tubing itself on the inside, being a moist, warm area, you can all begin to stimulate under deposit corrosion. So it begins to interact with the tubing itself, and now you begin to degrade that tubing. Scaling is a little bit different. A lot of times we see this in particular areas of the country. If you're in the upper Mississippi or down the Mississippi River Basin, out west sometimes when you're pulling from areas of limestone, you can get scaling. Now scaling, that can be calcium, that could be an iron, that could be a nickel. That's going to be something that once it gets inside those tubes and the heat of the steam goes across the tubes, it begins to dry that out and scale up the tube itself. So it's a harder substance. You have to recognize you have this problem because this later on we'll discuss about the proper techniques of removing it, but this takes a different technique than if you had a deposition type fouling. So this is something you want to remove because, one, it fosters removal of the scale because it has under deposit corrosion underneath the scale itself. It protects that so that it eats away at the tubing itself. You want to know what it is and what type of tubing you have so that you're able to get it out and get it out effectively and efficiently. The third is the microbiological fouling. Now this is a biofouling, and depending on the type of tubing you have, this can be very insidious. It attacks the tubing itself. It reduces your heat rate almost immediately. You can see the heat rate is going to be going down, but if it's left inside the tube, it can begin to eat away at the tube material. And so what you end up with is a lot of pitting that will actually eat down into the tubing and create a cavity between the ID and the OD of the tubes. And we're going to discuss later on in the eddy current section a little bit more about this and how you pick this up. But this is something that will happen, and you've got to make sure that you get rid of the microbiological fouling if you've got it in the water itself. Then there's debris and macrofouling. A lot of this comes in when you're at the ocean, at a lake, sometimes on a river. This will be shells. This could be wood particles. This could be aquatic animals, shellfish, leaves. It gets through the strainers, and then it plants out or plates out inside the tubing. And when it does that, it shuts off some of the tubes. And so now you have a very low flow going through down some of the tubes, sometimes no flow at all. But you also affect those tubes that remain open because now you cause eddy currents more in there, and that will cause erosion corrosion on the end. So it's something that you know if you have, you want to be able to get rid of it and get it out of your system. And then sometimes you get corrosion products, and these are just products that are within the water, interacting with the metal, corroding the metal themselves, and thus that creates a situation where you begin to have pitting and cracking within the metal. By corroding it, you make it weaker, and thus it's going to reduces its extended life. Now that you know the fouling 5, as we call it, you also have to recognize the type of tubing you have, because all these types of fouling affect metals differently. So if you have a copper, copper alloy, a stainless steel, or titanium, primarily the three we're looking at, each one of these different types of fouling affects these types of tubes. So a manganese, for example, which is a very thin, tenacious deposit, when we find that manganese usually plates out right against the tubing itself. If you have a stainless steel tube, manganese interacts negatively with stainless, and you can get a lot of corrosion and pitting very quickly. So you want to make sure that in a stainless tube that you remove the manganese because of that interaction. You can also end up with situations where you have two types of fouling inside the unit, where the manganese may be plating out on the inside and maybe a scale on top. So you're not really seeing the manganese, but you know that it's in there. We'll discuss how in a moment, but you want to make sure that you get it out and you're able to remove all the fouling in that tubes. Copper alloys are very, very good for a heat transfer, but they are also susceptible to microbiological fouling and to deposition fouling. Scaling can affect it quite a bit. So again, if you want to maintain the integrity of the copper tubing, you want to make sure you get in there and remove that before that fouling begins to interact with the tubing and begins to degrade it to a point where you have to start plugging those tubes. Now, we have seen in the past titanium is pretty much corrosion resistant. However, titanium doesn't have the heat transfer that a copper does. So as soon as you get the fouling inside that titanium tube, you're beginning to affect that heat transfer, which causes some issues on back pressure and therefore limits the effectiveness of the condenser and the plant. So again, good situation where you want to get in there and make sure that you remove all the fouling that is in that particular tube. So now you know that you're going to foul. You know you have fouling in your condenser. Every condenser does. Where do you fall in that fouling mechanism and what type of tubing you have? How do you know when you've got a situation that's coming up that tells you, hey, I've got a lot of fouling in the unit and it's beginning to degrade? One of the first is the back pressure. As the back pressure increases, you know you're putting pressure now on the rest of the unit, on the boiler and on the turbine, but it also gives you an idea that maybe your heat rate isn't working properly, and therefore maybe you have a lot of fouling in the tubes itself. Back pressure deviation is not caused solely, though, by cleaning, but in many instances, the cleaning will be the factor that increases that back pressure. If you have the sufficient amount of technology and data collection, you can do a cleanliness factor. Now, cleanliness factor is developed based upon the information that you gather from sensors throughout the plant, throughout that condenser, and if you have that already installed, you can run a cleanliness factor, and that with the back pressure can give you a very good indication of whether you have a dirty condenser or not. Another easier way, if you don't have the cleanliness factor, is just take a look at the inlet and the outlet cooling water temperature differential. As that differential begins to narrow and the back pressure begins to increase, that's a pretty good indicator that I've got a dirty condenser and have to start taking a look at a situation when I can get in there and clean it. Megawatt output is usually a situation where you're pressed to get the electricity out, you want to get the unit up and running, you don't have the time to clean the unit, you see your back pressure is rising, you see the inlet and the outlet cooling water temperature is decreasing. Now you've run into the megawatt output where you're starting to lose megawatts. A sure sign that the condenser is not being very efficient and that you've got to jump in there and clean that unit in order to get it back to peak efficiency. So now you've got this dirty condenser, you know you've got these problems, you've got some indicators there that are telling you, hey, condenser's dirty, I know what type of fouling I have because I've been on this river, this lake, this body of water for quite some time, and as we step back on that, usually the water source itself remains the same. So if you have a microbiological problem, it's going to remain there year after year. So you have a pretty good idea what's in there. But now your question is, how do I get it out? Which tube cleaner will work best with our condenser? Well, there are a variety of options, and in Total Performance, we're able to provide those options to you. You want to take a look at the tool you're using when you go in to clean. And it's just like any other project that you go into. You want to make sure you've got the proper tool. So you want to make sure you're using the proper cleaner. There are a variety of cleaners out there, but you want to make sure that you have the proper one picked with the proper size and the one that's going to do the job for you. An H brush, for example, which is a nylon brush, is very good when you have silt or mud and it's relatively light and you're able to remove it. However, if the silt or the mud gets too heavy, you clean the front part of the tube and the back part of the tube gets smeared because all that mud and everything gets clogged up in the cleaner itself, and it's not doing an efficient job. On that case, you're going to have to move to a heavier cleaner, maybe a metal scraper. If you have scale, if you shoot an H brushed on scale, you're just going through the process. You're really not cleaning the tube. You've got to make sure that you have a metal scraper. And what type of metal scraper? Well, there's a variety of types. Some are for a light scale, some are for calcium, some are for a heavy scale. And then you've got a stainless steel brush, which is excellent for manganese. So if you've got manganese in your stainless steel tubes, running a scraper or an H brush down them may not be sufficient. An H brush certainly not. You may require that stainless steel brush in order to get all that manganese out, because you want the tube to be extremely clean, because the cleaner the tube, the longer it lasts clean during the process. So how do you know exactly what you have in that tube? We recommend very strongly that before you get started, you take some shots, you shoot some tubes, and you shoot them with different types of cleaners. And you shoot these tubes around the unit. You don't just pick one area. And then you do an elemental analysis. Send it to a lab. I know we can provide that information for you, where this comes back and tells you what's in there. In this particular case, your manganese, 10 to 20%, so you know that's a large portion. And that manganese is probably plated out next to the tubing wall. You also are going to have some iron, silicon, and calcium, 5 to 10 and 1 to 5%. So you got scale, and that scale is probably on top of the manganese. What this report tells you is you've probably got a situation where you're going to need a tube pass cleaning. You're going to need a scraper of some sort to remove the scale, to remove the iron and the silicon and the light bit of calcium, and then a stainless steel brush to get rid of that manganese. That's the only way to really get rid of the entire amount of fouling in the tube and to protect that tube as you move forward. You also want to shoot in various parts of the condenser to do a test to find out, hey, what's the density in the tube? And tubes will be affected differently based on where they are. You may have a high density of fouling in the steam where the steam comes in. You may have it on the bottom part of the condenser itself, or maybe around the air removal section. So if you only shoot one area, you may end up with 25 grams. And therefore, you pick a cleaner that takes out 25 grams, not knowing that another part of your condenser, you have a tube with 126 grams. So you want to make sure you pick the proper cleaner for not only what you're cleaning, but for the amount of what you're cleaning. Remember, I told you the H brush is great when you're cleaning out silt and mud, as long as it isn't too heavy. Then you're smearing it. So you want to know that application up front. And what are the expectations that you want after you clean this unit? You want to be able to go in, you want to be able to use the proper tool, get all the fouling out of that unit, get those tubes clean as can be. And when you do that, you get an immediate performance improvement. When you start that condenser up, you immediately see that the unit is running at a higher efficiency. Your back pressure is down, your inlet and outlet water temperatures begin to increase, your cleanliness factor is solid, and the unit is running better, which means that efficiency translates to the entire plant. It's an effective deposit removal using the proper tool. Got to make sure you use that proper tool though. It protects that tubing against corrosion. It removes any obstructions that are within that tubing itself. It cleans each and every tube consistently, so you maintain that consistent cleanliness throughout the condenser. And it provides a smooth tube surface. Why is it efficient? Why is that important? Because the smoother that tube surface, the longer it remains clean and clear and effective before the fouling begins to compound again. If that tube is not cleaned efficiently, you already have a base for which the fouling will begin to interact and plate out on the tube itself again. Your additional benefits are economic. Now the unit is running efficiently, you're running effectively, you're reducing your costs, your fuel savings. Any recovered, any megawatts that you may have lost are now recovered because of the efficiency of the unit. And you now can reduce your CO2 emissions. So in today's day and age, when emissions are a very big problem and the EPA is on everybody's case, every power plant has them, we can reduce your emissions by having a cleaner condenser, because that allows your entire operation to run more effectively and efficiently, and therefore you're under control of your emissions. It also extends the useful life of the condenser. The last thing you really want to do is go to your management and say, you know, that condenser tubing we had that was planned for 20-year life, well, we're at 12 years, and within the next 2, we're going to have to replace it, all because we've got too much pitting, too much cracking caused by the fouling that was left in the tubes, because we either didn't clean or didn't clean the proper way. So you want to make sure that you can extend the useful life of that condenser, maybe even beyond the expectations. So in summary, from the cleaning side, understand your system. Understand how it fouls. Understand the fouling mechanism. Know that your tube material gives you insight to how it's going to be affected by the fouling that you have in the tubes itself. Pick the proper cleaner. That's the most important part of any cleaning process. By picking the proper cleaner, the proper tool, you're able to remove the fouling and get the unit back online and running effectively and efficiently. Because clean tubes relate directly to a condenser efficiency and a reduced cost, and also to a plant efficiency and reduced cost overall. So now that we know how to clean the unit, when we run into these problems where, hey, we've got a leak, how can I effectively locate a condenser air in leakage or tube leakage? Well, a total performance package can help you here. Why do plants need to test? Well, first and foremost, they need to test because, hey, they've got a leak. You know, the condenser is designed with an air removal section. And so even though the whole unit is supposed to run under a vacuum, that rarely occurs. There's just too many points of contact where you can get air into the system. And the designers know this. So that air removal system is designed to remove that excess air. The problem comes about is when you have a leak that exceeds the capacity of the air removal system to get rid of that excess air. And so now that O2 is now in your condensate, and it now is traveling down your system, affecting your boiler, your condensate, your turbine, and the efficiency and the effectiveness of your entire unit. So why do you need to test? Because you want to make sure that you don't have those types of problems in your unit. When do plants need to test? Well, number one, this is the call we get more often than not. I have a leak, my unit is down, or we're going to have to derate. Can you get somebody here immediately? We call that the reactive test. You've got a problem, you want somebody there now. Don't take a look at how inexpensive a flight is. Get on the next plane and get here. Can you get a team here in order to find this particular hole or in leakage problem? But we also recommend to have a proactive testing. And what do we mean by proactive? Well, one would be, if you have time, maybe a routine inspection. Remember, I told you, you're always going to have leaks in your system. It's always going to be there. So when somebody comes in and says, we guarantee to find a leak, they're going to find one because they're always there. The question is, do they find the right one? A proactive test will be able to tell you where those smaller leaks are. And maybe you can resolve that problem before it becomes a big problem. And when can you do it? How about before an outage? Before you go into the outage, before you start tearing things apart, you do a leak test, and that tells you where you have these small leaks. You're able to resolve that problem before they become a big leak. And they become a big leak in July and August when you're pushing the unit to maximum capacity. You're asking it to give you as much megawatts as you can. You're pushing it to its peak, and that small leak now becomes a bigger leak. Your air removal section can't compensate, and so now you've got a real problem, and you're back to reactive testing. How about after the outage? You know, you're in this outage, and you've done all this work. You've changed valves. You've changed flanges. You've put in test points. You've put in new sensors. All these areas can now be areas where you have air in leakage. So before you bring it up online, do a leak detection test. Make sure that you've torqued down all those bolts properly. Make sure that everything is sealed properly so that you don't have any air getting in. Make sure that the unit is ready to meet the challenge of the spring. So what are some of the indicators that you've got a leak? Well, mentioned this before on cleaning. Condenser back pressure is climbing. You've just cleaned the unit. You cleaned it in the spring. Here I am now in the beginning of summer, and my back pressure is climbing. It's probably not going to be a dirty condenser. We may look toward having a air in leakage into the system itself. As I mentioned here, there's other factors, but this could be one of them. Dissolved oxygen levels increasing. Maybe you're taking a reading of this in your system itself, and now you can take a look at this. And maybe an increased usage of phosphates. There are always signs. The condenser is always telling you what its status is. And you have to interpret that information to say, is that a cleaning problem or is that an air in leakage problem? And so when you do have an air in leakage problem, you want to address it quickly. And where can this air in leakage be? You've got a lot of sources. And this is where you want to have a company come in that's got a lot of experience. Because when you think about it, all the ruptured discs, the shaft seals, test probe penetrations, sensor penetrations, manways, vacuum pumps, flanges and bolt holes, think how many you have there. Every one of those is a source of air in leakage. And so there's so many that you want to make sure that the people you call are able to come in, talk with your maintenance team, and garner enough information that they have an idea where to start. Because if you're just picking and poking, you're going to be there a long time. But typically, an experienced crew will be able to find a leak within the day, or if you're in a large plant, maybe within 2 days. But there's a lot of points and a lot of areas where you can get air in leakage. So you want to make sure you cover them all and that the crews that you bring in are experienced. Now, water in leakage is a little different problem. It doesn't have as many points, but it still has its areas where you want to look to make sure that they're sealed. Water box flanges. Flanges are always a great place where you'll have water in leakage. We run into so many faulty tube plugs, and this just comes from a point where you're under pressure to get the unit online, you know you got to plug the tube, and so you put in a temporary plug in there, one that's to last a year, maybe 2, and you'll get to it next outage. Problem is, next outage you've got so much work to do that you forget about the tube plugs. 5 years later, that temporary plug begins to fail, and so now you have this faulty tube plug that allows water in leakage. Hot well components, through wall penetrations, tube to tube sheet joints. You know, when you're inside that condenser doing a cleaning, you should also get in there and take a look at the tube sheet. Inspect the tube sheet to make sure that it's weathering the storm well and that your tube to tube sheet joints are solid and good. You want to make sure that you do that because that's the source of water in leakage that can bring you down later on. So what are your critical factors? In air in leakage, you want to know the total amount of the air in leakage itself. What's my problem? What's the characteristic? Where's the air coming from? The leak quantification, that it really is a leak. You want to make sure that you've got the proper place that it's a leak, that it's not just something sitting in the system itself. Condenser tube leaks, you want to make sure that you can do online injections. You want to be able to find, in many instances, the condenser itself. It can be divided up into various boxes. Maybe it's 2 or 3 boxes. Maybe it's a 6-box unit. If so, you can do an online injection to isolate a box, and we'll talk about that a little bit later. You want a tube sheet inspection, as I mentioned before, because you want to make sure that the tube sheet is up to speed. You're not having a problem there. And again, what are my leak characteristics? What am I looking for? So what do we use to find these leaks? Well, number 1 is helium. Now, helium mass spectrometers developed to find small leaks in the Manhattan Project. And after that, it was used to find leaks in various other applications, and one of them was in the power industry. Helium is used probably in 90 to 95% of the applications. Why? It's quick, it's reliable, it's non-toxic, non-hazardous, easy to use, little paperwork, EPA's okay. It's got a very good detection range, 1 part per 10 million above background. So it's very sensitive, and you'll be able to find the leaks with this type of helium. It's suitable for most leaks, and we'll talk about that a little bit later. But I would say again, 95% of the applications use helium and use it very well. Another application, though, is SF6, sulfihexafluoride. This is a gas that was used as an airborne tracer to track plume migration back in the 70s. And EPRI brought it over into the power plants because it had applications that helium may not have been the right choice. Now, why was that? One, it's inert, odorless, and incombustible. But two, it's very sensitive. Where helium was 1 part per 10 million, SF6 is 1 part per 10 billion. That tells you don't have to use much, and it's able to find the smallest of leaks because of its sensitivity. It's non-reactive to H2O. We'll talk about this a little bit more, but we can actually shoot this underwater. So we can find leaks that are below the waterline. Helium, not as much. And its detection accuracies can be 40 times greater than those obtained using helium. So it's suitable for finding small or hard to locate leaks and for those leaks that are below the waterline. Now, you want to make sure that when you have a company in, you want to make sure that they're capable of doing helium and SF6. Again, 95% of the time, helium is going to work extremely well. But in those applications where SF6 is needed, you don't want to wait. You want to make sure you have a crew that is able to tell you right up front, listen, we'll start with the helium, but we've got to get some SF6 in here in order to find that leak that may be a troublesome or may be below the waterline. And what type of operating conditions do we need? Regardless of whether you're using helium or SF6, the unit's got to be running. You need about 15% of that turbine power. And why do you need that? Well, the steam flow is crucial to finding the successful leak because it pushes the gas down through the system. So you're forcing the gas down to where the leak actually exists. And that way you're able to sense that leak and pick that leak up. You also, it clears out the tracer gas. So now you don't have this buildup of helium or SF6 in an area. So you're not going to get some false readings. And then after you find the leak, it removes that gas from the system so that you get a quicker response time from the analyzer, and the analyzer's recovery time is quicker. So without steam, you're going to get this gas in the system, and it's going to be floating on its own. It may get to the leak, it may not. It may give you false reads, but it's going to be entrained in the system itself. So you want a little bit of power in order to drive this helium or this SF6 down through the system and then out the exhaust so that you find the leak and then you don't get false reads and you clear out the system very quickly so that you're able to find the leak itself. Now, how does that look? Whenever you have a leak detection team, you have a two-man team. You have one person that's sitting back at the analyzer, and you have one person that's out in the field sniffing. And so the analyzer is back there with a recorder. And as the gas is being released, there will be a point in time where the analyst says to the person in the field, the technician in the field, I'm getting a response. At that point, the person in the field stops because we have found a leak somewhere. We're getting a response back. And you get a rate of response, and that rate of response will tell you what type of leak it is, how big the leak is, what we've got to do about that leak. Now, as the steam continues to push the tracer gas through the system, you hit a magnitude, but then you begin to clear out. So that gas is now moved through the system, past the leak, and is now being exited. And once you get back to the baseline, now the analyst can say to the technician, from my recorder, it appears that this leak has occurred within the past 30 seconds or minute. Begin to retrace your steps and let's find exactly where that leak is. And that's the process they go through, and they're able to find that particular leak. Again, an experienced crew knows where to start. They'll ask some questions, they'll be able to jump in, and they'll be able to find the leak quickly. On the tube setup, it's a little bit different, but you go inside the inlet water box, and you can see here, goes through the air removal system, the condenser off gas, the sampling pump, the sample conditioning, the gas analyzer, and then through the exhaust. You also want to have an air mover in the outlet water box so that that gas is pulled through those tubes and exited out through the system. The gas is let down through the system until the leak is found. The leak comes up through the air removal system, the sampling pump, then drives it onto the sample conditioning system, to the gas analyzer, to where you have found a particular leak. In this instance, you can go through with these plenums, and these plenums are relatively large, and then you shrink them down. Once you find the area that the leak is in, you then begin to shrink the size of the plenum until you're down to 4 tubes, and then you do 1 tube at a time to determine which tube it is. Now, this is what I had spoken about a little bit before with SF6. It allows you to do an online injection into the water box under full load to determine what bundle is the problem. So you're able to connect to the injection point below the water line. The gas is then injected under that water line, and then you are capable of finding a leak that is equivalent to 1 gallon per day. A very small leak. Once you're able to identify where this leak is, you then may move back to the helium in order to find the exact cause of the leak, or where the leak is coming from. So in summary, for leak detection, air and water in leakage continues to cost generators hundreds of thousands up to millions of dollars every year. And condenser tubes cause more than 6,000 forced outages. Forced outages are not a good thing. So you get a lot of calls to say, listen, my unit is down, or I'm going to have to take a D-rate. You want to make sure that you have the proper team to get out there to help you, but you also want to do some proactive testing, and you can reduce the number of forced outages. So you want to make sure that you have a very good leak detection response team, you're ready to go with that, and that the ROI on this, in terms of maintenance dollars and operations, your ROI is in the 1,000 range. So you get a very quick return on investment whenever you do leak detection. And I will say, a relatively inexpensive process in order to make sure your unit is running efficiently. So now we've got it settled. We've got the cleaning of the tubes done. We've got our team ready to do the leak detection. We've done some leak detection. We know where we have problems. We've gotten some problems already resolved. But now comes the problem, how can I catch a problem within the tubes themselves, within the condenser, before they lead to emergency outages? Again, welcome to Total Performance. We're going to talk about eddy current testing. Eddy current testing is a non-destructive test technique. It's based on electromagnetic pulses that are sent back to an analyst, and that analyst, that technician, is able to read that information to tell you the status of those tubes without taking everything apart. So these probes are sent down the tube 100% of the way and back, and therefore that reading comes back and you're able to determine the status of your particular condenser. So what can be detected when these probes go down the tubes? Well, a variety of different defects. Pitting, cracking, you can find erosion. Have you got erosion problems maybe on the ends of the tubes? Corrosion issues. You've got corrosion products. You've cleaned it out as best you can, but maybe you have some corrosion issues down the tubes, further down that you can see. You can see grooving. You can see dents. So an experienced crew is able to come in, gather the information, and then tell you what you have there. Now, why do you want to do this eddy current test? What does this do for you? Okay, I know the condition of my tubes. Well, it decreases forced outages due to tube failure. You're able to plug these tubes prior to them failing. You're able to see that particular tube and what's causing the problem. So you minimize your losses associated with the availability of the unit itself. So you're able to early detect potential failure mechanisms. You're able to plug those particular tubes and maybe resolve the problems that you have prior to this reoccurring. Maybe you can increase your cleaning schedule. Maybe you can work with your people that are treating your water treatment program, in order to alleviate some of these problems. You also can estimate the remaining useful life of the tubes. Again, you don't want to be able to go back to your management and say, we have such a problem that we need the budget to retube this unit in 1 or 2 years. In this way, you can read, what's the situation in my unit? How much useful life do I have? And therefore, I can budget and plan when I need to replace the tubes themselves. So you're going to get a summary of the entire unit and know the status of what's going on. What are the testing requirements you're looking for? One, you want to make sure you have a certified team. You want to have them certified by the American Society of Non-Destructive Testing. You want to make sure that they have a quality assurance program, and that quality assurance program meets industry guidelines, or at least your guidelines. Maybe yours will be even higher. You want to make sure that they have the current equipment. You don't want it old. You want to make sure it's current equipment with current software, and that it's calibrated properly. And you want to make sure that the tubes are clean. And I have a slide later on that will show you why clean tubes are very, very important. Now, there's various pieces of equipment out there. This is one of them, the CoreStar Omni type of equipment that can be used. So you have that as your analyzer. You have your probes. The probes are going to be purchased based on what you're looking for. Are you looking for erosion, or are you looking for cracking? The tubes themselves should be 85% fill of the tube. So the probe, when you push it down the tube, should fill that tube up to 85%. Otherwise, you're going to get a lot of bounce in there, and you're going to get some erroneous readings. So you're looking for 85%. Reason one to clean the tubes, you don't want the probes to get stuck going down the tubes and to be broken as you try to move them forward or back. So allowing enough access for the tube to get down, or the probe to get down the tube, is one reason to clean. And you want to make sure that you have computerized data so that you are able to read this information once it is all collected. There are also two methods here. There are two modes, if you will, whenever you do eddy current testing. One is called the absolute mode, and that's for erosion. So if you have this erosion from the front of the tube as it leads into the condenser, that's going to be a gradual process, and so you need the specific probe and the mode, the absolute mode, in order to read that erosion. The other ones are the differential mode, and a differential mode is going to see immediate change. A pit, a crack, that's going to be an immediate change that you're going to sense as the probe moves down the tube itself. And so that adjustment there is going to be noted in the differential mode. You need both of these if you're going to be looking for wall thinning and or cracks or pits. Now you also want to make sure you have multiple frequencies. It's a little bit misleading. Multiple frequencies is more than two. If you only have two frequencies, you're going to be able to say, I found a pit, but that's about it. If you have multiple frequencies of 4 or more, you're going to be able to see the entire tube, because a frequency only can travel so far. It's going to see the ID of the tube. Another frequency may see the OD of the tube. Other frequencies may see the center part of those tubes. So you want to be able to see the entire tube. You need multiple frequencies so that you can identify whether it's an ID or an OD pit, and do it simultaneously. You want to be able to see the complete depth of the penetration of the tube wall. And I'll show you a picture in a moment that will show why. You want to be able to accurately characterize the defect. Is it just a pit, or is my tube wall being eaten out? It allows for mixing out of signals that represent support plates, because a support plate is going to give a signal. You want to be able to have enough frequencies to say it's a support plate, that's not a pit. And it also allows for discrimination of metallic deposits. This is the picture I was speaking about before, this could very well be a microbiological fouling or a manganese within stainless, where if you only have 2 frequencies, you're going to see that as just a pit on the ID of that tube. You are not going to see that that's a cavern in there. Multiple frequencies tells you that this cavern has caused this tube to only have about 10% wall left. That's going to fail. So this is a tube that's going to be plugged if you have multiple frequencies, probably left alone if you don't. This is also a case where this is one where you want to make sure you have the good cleaning. You want to know, I got stainless, I got manganese, I've got microbiological fouling in copper tubing, because this is what you end up with. And if you don't get it out, you're going to end up with a lot of tubes like this. Now this is a real case for cleaning the tube. This is the same tube. The left and the right are the same tube. The one on the left is prior to cleaning, and the one on the right is after cleaning. The most experienced technician is going to have a very difficult time making a call on all the data that has come back on that left-hand screen. It looks like you've got a tremendous amount of pits or cracks, deficiencies, defections within that tube itself. And you're going to end up plugging that tube based on that data. However, when you look to the right, you see that you don't have that issue. You have a support plate. You may have a small defect within that unit itself, but the tube itself appears to be pretty good. And so you have useful life within that tube. You want to be able to have the tubes clean so that the eddy current can make the proper call on the unit itself. And you want to make sure you get a report. That report's going to give you an executive summary of the condition of the unit, a detailed data on each tube, a color-coded tube sheet map, and on-site analysis if you want it. Why do you want on-site analysis? If you want to plug this unit up and you want to get it back in operation and you don't have time to wait, you're going to want to have the analyst on site that's able to read the data, tell you right then and there what tubes need to be plugged so that you can plug it and move forward. Now this is the detailed data, and you should get this with every tube that's tested. This will tell you the section of the condenser, tells you the row and the tube itself. It'll tell you voltage, and voltage tells you how big the defect is. How large is that defect? The degree tells you whether it's an ID or an OD, and it gives you a percent wall loss. Very, very critical on percent wall loss, and we'll talk about that in the next slide. It also tells you the location. So it can say to you 12 feet, 3.5 inches down this tube, you have a pit in a certain location within that tube. And you are then able to determine how much wall loss do I have, should this particular tube be plugged or not. It also gives you the ability to pull a tube and then cut the tube to analyze whether the data that you're getting is accurate. And we recommend that on occasion you do that. And then of course the tube sheet map. Now this is something that you should keep. You should get it, you should keep it filed, because this is a wealth of information. This tells you exactly what's going on in your condenser. So how much do you test? Initially you test 100% so you have a baseline, and then maybe you only start doing 10% per year. And you will do that throughout the condenser randomly so that you have an indication of what's going on within your condenser. But as the condenser ages, and as you begin to get this report back, you can see in the upper left-hand corner, that's probably where the steam dump's coming in. We've got a lot of plugged tubes. We also have a lot of tubes with wall loss. And then down in the center, on the top of the air removal system, the same problem. So you may want to increase the number or the percentage that you're testing to 15 or 20% and focus more on those areas, because those are problem areas. This tube sheet map can then be handed to any respectable eddy current technician, and they should be able to read this and go over it with you and then make decisions how best to move on. Now, the last thing we want to talk about here is plugging. I can't tell you how many times we've gone into a situation where we have presented all this information to the customer. And by the way, you, the customer, make the call on what gets plugged. You're the one that says 80%, 50%, whatever the number is. This is what gets plugged. where they want to have tubes plugged and they don't have any tube plugs. And so the order has to go out now. Our recommendation is pick the plug that you want, that you think is best suited for your application, and keep 2% of those in your inventory. That way those can be pulled out when needed. The tubes can be plugged, the unit can be put back in operation, and you, at your leisure, can then go back and reorder the plugs for the next time out. So having the proper plug in there is very important, and that is a discussion unto itself because there are a lot of different types of plugs out there. So what are we trying to do here in summary? Reduce the number of forced outages due to tube leaks. We want to have an early detection of a potential failure. We want to know how long the condenser is going to last and the overall condition of that condenser. That's what you're going to get from eddy current testing. So in summary here, the plan here is to have a plan of attack whenever you do cleaning, eddy current testing, and leak detection, so that it's imperative for you to have your condenser running at peak efficiency at all times. You need to have all three of these mechanisms in place. The plan is to implement a cleaning and testing program that you follow, and that may be once a year, that may be twice a year in some instances, but you want to have it so that the unit is effective and efficient and operating when you want it to operate, and you reduce those unwanted and unexpected repairs down the line. I know I've presented a lot of information to you, and I appreciate your time. Thank you very much. This will end our webinar, and we will move now into the question and answer section. So thank you very much, and we're open to questions.
Thanks, Gary, for your presentation. We've had several questions come in from the audience during the program. We'll try to answer as many as possible with the time remaining. If there are questions we're not able to answer due to time constraints, we will try to answer them individually by email after the program. We'll start with the first one here. Do you take experience, and I think they mean, do you have experience with the terephthalate acid plants?
You know, that's an interesting question. We're going to have to get back to this gentleman on that. We do power. I am a power guy, so all we do is on the power, but we do have an industrial division, and I will talk to them specifically. I don't know the answer to that, so I will have to get that from them to see if they do, and we can have somebody respond to them after this is over. Sorry about that, but I just don't have any experience on that end.
Next question here. What's the optimal solution to clean the U-tube?
We have U-tube cleaners. What you want to do is you want to analyze what is in those particular tubes. There are two ways to do it. One is the U-tube cleaner, which you shoot the same way you shoot a regular cleaner using water, and it will go around the U-tube. We have a metal, and we also have one that's a polypropylene type cleaner. So depending on the type of U-tube that you have, we can usually shoot these into the bottom 2 or 3 rows. When it gets to the inner 2 or 3 rows, not bottom, but the inner 2 or 3 rows, that bend is so tight that sometimes we can't get the cleaner around it, so we avoid doing them, but we can shoot all the other tubes. The other way is to use a rotary brush called an Excalibur, where you actually clean each tube independently by pushing a rotary brush down each tube and cleaning those tubes out. So we can do either way on a U-tube cleaner. But we do quite a few of them, and we use them both applications.
Thanks for that, Gary. Next question, how do you determine the total amount of air in leakage?
Well, to read that, there's a couple ways really to do it, and I wish I could tell you that there is a specific way to give you an exact number. But you can take a look when you do the leak detection, as I was mentioning, and as you see the curve, you'll be able to ascertain from that curve, from how high it gets and also how wide it is from the base, the information you need to tell you how big that is. That's not going to give you a specific figure, but you're going to be able to see how much total air in leakage you have at that particular point. There's also programs out there that can run based upon instrumentation that we know of. We don't have that, but there are others out there that have instrumentation that you put in your plant, and you read that data. That data is then brought back into a system that calculates for you and can tell you how much air in leakage there is. And if you're interested in that, please send me an email, and I will get you to the proper person that can help you with that.
Okay, next question. Would you be able to differentiate among cracking, pitting, under deposit corrosion, etc. via eddy current testing?
Yes, you should. If you do the eddy current test and you use the multiple frequencies, an experienced level 3, which you should have, or a level 2A, should be able to take a look at the data and see whether you have a crack or whether it's a pit. Under deposit corrosion will come out once you have it removed. Of course, you've got to remove the deposit, but once you remove it, you can then see what is occurring there, whether it's a pit or whether you're just corroding the material itself or whether you've got cracking. If you have the proper probes, you can also tell whether you have erosion corrosion or a thinning of the tube itself, and you can, through eddy current testing, determine how much thinning that is. And that's what eddy current testing will give you. It'll give you all that information: how deep's the pit, how deep is the crack, is the crack all the way through, is it repairable, so forth and so on.
And as a follow-up there, can the eddy current test be used on all tube types?
Eddy current testing is used on non-ferrous. Because it's an electromagnetic pulse, you can't have a ferrous tube material. However, eddy current testing is a subset to non-destructive testing, and there are many types of non-destructive tests out there. One of them being what we call RFT, which is remote field test. And the RFT is what you would use on a ferrous tube. So eddy current, no. RFT, yes, you can on the ferrous tubing, and you can read and see much of the same type of defects in a tube using RFT. It's a little slower process, a little different process, but still very, very capable and used in many instances in the industrial arena, that along with iris testing, which is another NDE process, because they use ferrous metals in their tubing itself. So eddy current is a non-ferrous technique which we run into predominantly in power.
And how often is it recommended to perform these eddy current tests?
Okay, what we recommend is when you have your unit up and running, if you have not done a complete test, we recommend that you do a complete test of 100% of your tubes to get a baseline. Then, depending on the test results, you should do in increments of 10, 15, 20% every year. And if you do 10% on a new condenser over a 10-year period, you will have tested every tube once. Once that map begins to populate, you start to see areas where you have degradation of the tubing for one reason or another. That's when you begin to increase the percentage up to 20% or 25 or 50% in order to make sure you know the status of those particular areas in your condenser. Remember, the key here is the ability to keep your unit up and running at all times, especially when you're pressing it to its peak performance in the summer months. That's when you're going to have the tube leak. So you want to make sure that you have everything covered. So as the unit gets older, you want to test more. We recommend that you test a portion of that condenser every year. You put some money aside to do that.
And we have time for one more here. Would you specifically address fouling for air coolers and condensers?
Sure, and I think what you're talking about here is an air-cooled condenser. And if I'm wrong, I apologize, but an air-cooled condenser has a different type of fouling because it's got finned tubes. They're usually in A-frames with large fans underneath them. These fans bring in everything that's underneath on the ground, and so you'll get pollen, you'll get dirt, you'll get debris, leaves, plastic, and they plate up into the fins, and then they push into the fins themselves, plugging the fins. There's a mechanism out there that we have, an automated cleaning system that you can attach to the top side of those fins, of those A-frames, and you can clean those air-cooled condensers, removing all that debris between the fins so that you get that peak performance back. You can do that on an A-frame, or you can do that on a flat air cooler, either way. So there are ways to get rid of the fouling that is impacting those particular units.
Thanks, Gary. Thanks for those great answers. Thanks to the audience for all their very interesting questions. We're approaching the end of today's program, and as mentioned, we'll address further questions individually by email. Also, if you want a copy of this presentation, Gary's contact info at Conco is on the slide there, so please reach out to Gary at Conco with any of your other questions that you may have, and to get a copy of the presentation. We want to thank Conco Services Corporation for sponsoring today's event. Thank you all for attending. We hope you'll benefit from today's presentation, and go out and have a great day. Thank you.
Thank you.